framework. Metal organic frameworks are class of crystalline materials. They form by metals, or it could be a metal ion or metal cluster. They're connected with organic linkers, okay, in three-dimensional space, and they give very high porosity. What is here, if you see this design strategy, this blue color, these are the metal ions or metal clusters. They're connected by these red rods, which are nothing but a ligand. That ligand can connect in the both end at 180 degree, this side as well as this side, okay. So this is one of the unit of a metal organic framework, and if you keep connecting them and keep repeating this unit, they form a three-dimensional structure in space, okay. Now, what is the advantage of the metal organic frameworks in terms of design? You can choose the metal ion you would like to use based on your preferred property, like property you would like to see in your material. You can choose the ligand. You have the option to choosing the ligand, okay. Therefore you can control the physical and chemical properties of the materials, okay. Now, if you think about, oh, really, is it easy, or it is? Actually, I'm getting a lot of background noise. Is there any problem in the system, or hello? 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 Actually, I'm getting a lot of noise. Hello? May I request you to mute your microphone? Otherwise, I am unable to speak. Hello? Okay, let me continue because I was getting a lot of background noise and unable to speak. So I hope you people have muted it. So it should be fine for me. So anyway, let me continue. What I was talking here, the design strategy for a metal organic framework based on the choice of the metal and the ligand, you can actually control the chemical and physical properties of these highly crystalline materials. There are many advantages of this material compared to other porous material. For example, these are the materials which can be prepared very easily, okay. See, if you take zinc oxide, which is very easily available, and with this terephthalic acid, heat it in diethyl formamide at 100 degrees centigrade for few hours, you get a pure crystalline material of this structure having the surface area of 6,000 meters square per gram. Now, question is that you are having 6,000 meters square per gram surface area, means in 1 gram of material having surface area of a roughly size of a football ground. How is it possible? Is it really practical to think like this? Is it possible? And it is highly possible. See, you think about a room, a big room. In a big room, you have only 4 walls. Okay, sorry, 6 walls. Here one, here one, here one, here one, at the back side one, on the front side one. So that's your surface area. Now you put some wall in the middle of the room. So the moment you put a wall, you created more surface area. You put another wall somewhere here. You put another wall somewhere here. You put another wall somewhere here. So these are the vertical walls. Now you start putting the horizontal wall somewhere here, somewhere here. The more number of walls you start putting, you're actually creating more amount of surface area in any material, right? Anywhere in the space. Now, if you keep adding the surfaces like this, so you think about a big room and you start putting the matchbox. Okay, you put it, you just loaded with the matchboxes. Each matchbox is having some square centimeter surface area. Okay, when the room is loaded with this matchbox, the surface area is very high. It's not only the 6 walls, there are many more surfaces available inside the room. Similarly, here, if you have a material which are having the wall size or the opening of the size of the nanometer, the surface area goes to the extreme high. Therefore, it is highly possible to get the size of a football ground amount of surface area in a gram of material. Okay. So this is one of the very famous MOF. We call it MOF. It's the term is invented by Professor Omori Yagi. He is currently at the University of California at Berkeley. So this is one of the MOF, and if you change the carboxylic acid, you change the metal ion, you get a different porosity, different surface area, different chemical property, and maybe the different physical properties. Okay, that's the advantage of metal organic framework over any other porous material. You can get a crystalline product, you can get a very well defined pore size, you can get very well defined surface nature of the surface property, you can get a very well defined the chemical property due to the choice of the metal center. Like I chose zinc here, I chose copper here. Like it's not me, it's Yagi's compound. Okay. Now, in another example, in this example, if you see that the numbers MOF 177, MOF 180, MOF 200, these are the number given by Professor Omoriagi. He just actually coined this term, and this is his numbering. What to learn here in this slide? If you see this slide, these MOFs are made of with the zinc cluster. Here, the metal is a zinc cluster, small cluster, and they're connected with different carboxylic acid. It is in triangular. Say, for example, the ligand is here. The metal will be binded to the ligand through this carboxylate, and they're at 120-degree angle. Okay. So two things to be noticed here. The pore can be not only kind of a box shape, it can be spherical shaped if you choose this angle of coordination here. Here it is one coordination, another, second one, third one. So these three positions are connected to metal to decide the nature of the pore. Okay, like sorry, the shape of the pore. At the end, you get a very spherical kind of pore. It's not a rectangular. Therefore, what I'm trying to tell you that if you choose the right geometry of the ligand, you can actually design the shape of the pore. Not only that, now you have a lot of organic moieties are there. Okay, now the nature of the nature of the surface of this compound will be depends on the nature of the ligand you have chosen. It could be hydrophobic, or it could be hydrophilic, it could be something else. You can put a functional group here, you can modify this whole area of the ligand, and based on your modification, actually you can design, you can predict, or you can expect some chemical properties of this particular class of compound. And best part of this compound is that once you get the compound, the nature, the shape, size, chemical property, and physical properties of this each pores are uniform and perfectly fine, like in terms of homogeneity. Okay. Now in nature, there are a lot of other porous materials. For example, our lungs is a porous material. It made of porous materials. Corals, sponge, even the chalk you use in the classroom, cloths, all these are porous materials in nature, and all of them do a particular like they are meant for, or they're designed for a particular property. Okay. And but what is the advantage of then metal organic framework compared to those porous materials? See, those porous materials can do a particular job. Like your lung cannot do the job of a sponge, or your sponge cannot do the job of a chalk, or chalk cannot perform the job expected for a cloth, for example. So they are designed for a particular purpose. But the advantage of the metal organic framework is that you can design the property, like based on your choice of ligand, choice of metal, you can try to get the property you would like to see in your material. Okay. So in these presentations, I'll be quickly going through some of these properties. For example, properties of carbon dioxide sequestration, hydrogen storage, sensing, proton conduction. Maybe catalysis I will exclude from this talk. Let me start with first property of carbon dioxide sequestration. What is the problem of carbon dioxide? All of you know it is a big problem in terms of global warming. So what if you put a carbon dioxide inside a, say for example, in a gas cylinder, okay, store it in a high pressure, you can do that. So carbon dioxide is stored in a cylinder, and you throw it in somewhere. So your carbon dioxide is inside the cylinder, it is not in the atmosphere. But it is not a practical solution. Why? Because the carbon dioxide create lot of pressure on the wall of the cylinder due to high kinetic energy. Okay, so you can put a very limited amount of carbon dioxide inside any cylinder. Now you think about MOF 177. I think last slide, the first example I mentioned was MOF 177. So you know that that is made of a zinc and a particular tricarboxylic acid. Okay, here it is. Okay, yeah, it's already given over here. So when zinc is combined with this particular tricarboxylic acid, it forms a highly porous crystalline material, which is given the name of a MOF 177. Now, if you load this MOF 177 inside this like standard cylinder and try to put the carbon dioxide, the amount of carbon dioxide it will store is actually 9 times than if you do not put MOF. Now, this is a very interesting question. See, initially I had empty cylinder, and I am telling you that it is taking less amount of carbon dioxide, okay, compared to when I have already filled the cylinder with MOF 177. How it is possible? Because it is already now containing MOF 177. Empty is able to take only one equivalent. Now, once I put MO 177, it is taking 9 times more. What is the reason? Reason is that, see, when you have a gas, due to very high thermal like kinetic energy, the gas molecule hit the wall of the cylinder, so they can create a lot of pressure. Okay, therefore there is a, it will, if you can't keep certain amount, like limited amount. Now when you put this highly porous material, now you have lot of surface inside the cylinder, lot of small compartment inside the material, therefore inside the cylinder itself. Now by doing so, you are actually restricting the velocity, the free movement of the carbon dioxide inside the cylinder, therefore it increases the storage capacity. Not only that, what they have done, they have studied not with the exactly same MOF, but with different MOF, that this carbon dioxide is actually getting attached to the metal center inside the pore. This is the our pore here. These are the zinc center. These are connected with, this is, no, sorry, this is magnesium, not zinc. These magnesiums are connected with this dicarboxylate, and there is some coordination sites available for the magnesium. Therefore, when you push carbon dioxide inside this material, the carbon dioxides are connected. See, each unit is connected with 3 equivalent of carbon dioxide. Therefore, it restricts the velocity of the carbon dioxide, movement of the carbon dioxide, so it can store more amount of carbon dioxide compared to a empty cylinder. Okay. Now, there is another angle of this work, very important angle, is that hydrogen uptake. Okay. Why hydrogen uptake is important in terms of material applications? Because you know that hydrogen is a green fuel. Okay. Uh, it burns, give you very high energy, and as a byproduct gives only water. So it is a non-pollutant green fuel. But when you store hydrogen inside a vehicle, it has to be, practically possible to run the vehicle to certain distance. For example, if you want to run the vehicle up to 400 kilometer, it needs 3 kilogram of hydrogen. Okay, to burn, to give you that much of energy. Now for storing 3 kilogram of hydrogen, you need a cylinder of the size of roughly 2 meter by 1 meter, and the pressure should be 350 bar, extremely high pressure, big cylinder 2 meter by 1 meter to store 3 kilogram of hydrogen to burn and give you the enough amount of energy to run your vehicle for 400 kilometer. Then it is fine. Now where is the problem? Problem is that the size of the cylinder is very big. The pressure you need is extremely high, 300 bar, 350 bar. Therefore, it is not practically possible to use such cylinder inside the car because of the chance of explosion at high temperature. Okay. Now, what is the solution? Solution could be again MOF. Now it is with the MOF 210. What is MOF 210? It is made of zinc and simply 2 carboxylic acid. at, you just cook it at 90 degrees centigrade for 72 hours. It gives a beautiful molecule with three different types of pores. Okay, they have given in three different color over here. And again, this MOF was reported by Moriagi in 2010. What this MOF does, it can take the 8.6 weight percentage of hydrogen at 77 Kelvin and 80 bar. Okay, so if I correlate the practical application, you need roughly like 8 percentage weight percentage of hydrogen storage for any MOF at 20 bar pressure at room temperature. That is the practical application you can use for any material for hydrogen storage and apply in generating energy. So this is not the perfect result. Weight percentage is fine, but here temperature is 77 K. This temperature has to be at the room temperature, and this pressure has to be 20 bar pressure. Therefore, lot of research is still going on to improve the storage capacity of these molecule, of this metal organic framework for towards hydrogen. Okay. Now, again, you can ask me, sir, if you have a empty cylinder, you need a much bigger cylinder to store same amount of hydrogen. If you do not put your MOF, okay, now you put MOF, it is storing more. How it is possible? Again, the same explanation. See, if this hydrogen moves very fast and hits the wall of the cylinder, so they exert a lot of pressure. Now, if you put MOF, means you're putting very small nanometer size compartments. Okay, and that actually restricts the movement of the hydrogen. Now, some studies are done with a MOF 74. It is due to Newton diffraction. It's called Newton diffraction pattern, which gives the accurate position of hydrogen in any material. Okay, so in MOF 74, they find out that this is the pore. This is your. This is the ligand. This is the metal. These metals are connected with another ligand. That ligand is connected with another metal, therefore generating a very big pore. Now, when hydrogen was given, you can see that the position of the hydrogens are now localized. These greens are the positions of the hydrogen. 1, 2, 3, 4, 5. They are not moving too much here and there, not creating too much of pressure. Now, when pressure was increased, it has been observed that the more number of hydrogens are being stored inside the cavity, and it's kind of forming layer by layer. First the green one, then blue one, then yellow, and then pink. So more numbers of hydrogens are getting the restricted into the each pore. Therefore, the storage capacity of hydrogen inside the material is also increasing. Okay, so now you can ask me one question that first let me show you some practical applications. So these are the these are the picture taken from website of some US government website. This picture is from California, where you can see that these are the size of the cylinders in a car, which is much smaller than 2 meter by 1 meter. Okay, at the back position over here, and they loaded with MOP 74 and pumping hydrogen from the cylinder. So the material is storing hydrogen and it is releasing slowly to get burned and generate the energy for running these vehicles. Okay, and this is the picture from London. You can see at the rooftop of the bus. This bus is running by hydrogen fuel. So these white colors are the cylinders which kept hydrogen and then generate energy for this particular bus. And this is a practical application. It's not like futuristic, or it is too difficult to achieve. And very clearly labeled. This bus is clearly labeled as hydrogen bus. Go green for London. Okay, perfectly fine. Now, one question you can ask me: hydrogen is extremely, inflammable. It can catch fire and generate a lot of energy. So, is it really safe to store hydrogen like this, the way I was demonstrating, and use it? The answer is here. This picture, if you see, this car contain a cylinder here over here, hydrogen containing hydrogen cylinder, and this is a car having a gasoline tank, means petrol tank. Now both the cars are like use some fire to create some flame. And if you see, for hydrogen, the flame is going straight vertical. The reason is that hydrogen is much, much lighter than the air. Therefore, hydrogen will be, coming out straight vertically. Therefore, therefore it is not going to do much harm compared to a vehicle which is having a petrol tank. Therefore, comfortably we can conclude that storing hydrogen is much safer than using a gasoline tank in the car. Now, coming to another applications of this metal organic framework is the sensing of small molecules or explosives. That is another aspects of these materials. What is sensing? What is detection? If you have done any flame test in your 12th standard school, or even in your BSc college, what you have done, you took probably some small amount of sample, unknown sample, then you have given a platinum loop, you dip into a dilute or 6 normal hydrochloric acid, then touch the sample with your platinum loop, then you expose that sample to a non-luminescence flame, then you see different color, right? If it is say big red, you say, oh, I got calcium in my sample. If you get say crimson red, then you said, okay, I got lithium. Or if it is bright yellow like this, you conclude, okay, my sample is having sodium. Like you can do simple test to detect different alkali and alkaline earth metal content, metal ions contain into your sample. Why it is happening? Because when you burn it, first you add HCl so that it forms a chloride salt, which is kind of easily evaporable. And now when you burn in a flame, the electron from the inner orbital, they go to the excited states, and then they come back to again to the ground state. In the process, they release the energy. Okay. And for each metal, the energy gap between the excited electronic, like higher orbital and lower orbital, is distinct and different. So they emit a particular wavelength and you get to see different color. Okay. But it's not very it cannot be applicable for organic molecules. It cannot be applicable for many other complexes or chemicals. In most of the cases, you have to use some spectroscopic technique, for example, NMR, IR, UV visible spectroscopy, fluorescence, and many other complicated techniques. So is it possible to design a molecule which will give you naked eye detection, means without using any instrument, you just expose your sample and it will tell you by showing some color changes or some physical property changes and detect a particular chemical? Is it possible? I don't need to use any instrument, even a simplest one like a flame, like you need a flame basically to do the flame test. Is it possible? And metal organic framework has some solution at this point also. Let me give you why any metal organic framework or any chemical gives you color. See, when you see the color can be due to some charge transfer. Okay, the charge transfer can be from ligand to metal or metal to ligand. You know that it is known as LMCT or MLCT. Or your metal can emit some light. Okay, which we detect in UV visible spectroscopy. Or if you have a conjugated system, organic moiety, that also can emit some light. So these are the possible reason why do you see color in any metal complex or in a metal organic framework. This is a single unit of a metal organic framework. Now you imagine that in a metal organic framework, as I mentioned, these are the highly porous crystalline materials. So you have a pore inside, big pore inside. Now you put a chemical, some chemical. Okay, what this chemical can do, it can interrupt or it can have some interactions with the ligand, with the metal, and it can disrupt this whole charge transition process or the emission process that was going on earlier before you have this particular guest molecule inside the cavity. Therefore, due to these interactions or interruptions, whatever you say, you may see some change in color in the molecule. But it's not the case always happens, because most of the times the guest molecules don't go inside the cavity. Even they go, they don't interact enough to see or to have some impact in terms of change in color of this molecule. Okay, but in case you have a very nice porous molecule that encapsulate the guest molecule, and the guest molecule interrupt with the these charge transfer processes, so you can see some color changes. Therefore you can identify or you can detect that particular chemical. So you have wonderful results in this area. So our whatever I am going to talk from now onwards, it's mostly our own result. The research was done in ISA Bhopal. Uh, okay, so I'm going to present to you one molecule that detects very clearly the largest possible number of small molecule chemicals, nitroaromatic explosive, just by changing the colors. If you see the change, different molecule are encapsulated and color is different, therefore you can identify the molecule. Let me start with the actual molecule we have prepared in our lab. What we have done, we have reacted cuprous iodide in presence of potassium iodide with this V-shaped torpedidyl ligand. Why it is V-shaped? Because these are the three nitrogen which can coordinate to the metal center. It's a very simple reaction. You cook them for a few days in presence of dimethyl formamide and acetonitrile, and you get a very nice framework structure. The framework is made of cuprous iodide. If you see this part, these are two copper center. These copper two centers are connected with iodide, and these two centers are connected with two ligands in two different directions, two opposite directions. These ligands are connected further with the more cuprous iodide to give you a two-dimensional sheet structures. Okay, and these two-dimensional sheets are kind of interdigited with each other. Like blue is like it's going in between the red is going in between, running through the green, and therefore it is forming a kind of three-dimensional structure. So initial color of the complex was bright yellow, as I have shown here. Now due to these weak interactions between these two-dimensional sheets, it's actually formed a three-dimensional structure having a cylindrical pore here. If you see, this is the cylindrical pore present in our molecule. And this is the cross-section of this cylinder. When I cut it one side, I can see we are having one DMF and one acetonitrile, and size of the pore is roughly, I think 8 by 9 angstrom, and the whole molecule is kind of as I mentioned, the two-dimensional sheets are getting like stick together by pi interactions, ch pi interactions, etc., to form a three-dimensional structure. Perfectly fine. So when we made the molecule, it was originally was DMF and acetonitrile, but when we left the molecule outside for half an hour or 1 hour, we can see the bright yellow color of the molecule is changed to bright green. Okay, but still it remains as single crystal. By the way, for the students, the structures I am showing you here are obtained from a technique known as single crystal structure. Okay, you need a single crystal, means like a sugar. Okay, sugar cube, and if even it could be much smaller than a sugar cube, you put into a single crystal diffractometer and the X-ray, single crystal X-ray refractometer. Now X-ray give you the position of the atoms, the bonds, and all the things. So whatever I am going to show you now, these are the structure obtained from single crystal X-ray crystallography. Okay, now once these DMF acetonitriles are removed, not removed, what happened when you keep it outside atmosphere, the acetonitrile comes out and the acetonitrile positions are occupied by water molecule, and the color is changed to green. Then we realize that if acetonitrile is being replaced by water, the color is now green. So what about all, like there are many other solvents and chemicals? Is it possible to exchange these guessed DMF and acetonitrile inside to see different color? Okay, and this phenomena is not very regular in normal chemical research. So what we have done, we have done some very simple homemade experiment. We took crystals. Original crystal was bright yellow in a vial, small vial, and we put it in a bigger vial, and in the bigger vial we put different solvents, okay, and we seal the bigger vial. That means we expect that, for example, here acetonitrile or DMF, they will slowly diffuse into our crystal here in the small vial, and we expected to see some change in the color. Okay, here it is DMSO, acetonitrile, DMF, methanol, chlorobenzene, fluorobenzene, chlorobenzene, bromobenzene, iodobenzene. We have done a series of experiments, and what we found really, like, it's a wonderful results. In each cases we can see that the single crystallinity, generally it never happens, the single crystal remains a single crystal, so that we can characterize them structurally. Not only that, without doing any single crystal structure analysis, I can see the distinct color. In each cases it is showing a different color, so that I can tell you that, oh, it is chlorobenzene or bromobenzene, whatever colorless liquid you give me over here. If I don't know, without doing any experiment, I can tell you what is the chemical actually you have given me. Now let me go to the further details. See, here it is DMF color is, DMF and water color is green. When is it is the DMF water is being replaced by DMSO, color is bright yellow. Now it is replaced by methanol, color is green, pale green. Now question is that, see, if you give me a sample or any some liquid solvent, I don't know what it is. I just expose your unknown solvent to my crystal or to my material. Here, this is the like color of the materials, and I can tell you without doing or without taking any help of big instrument, that what is the identity of that particular colorless sample you have given me. Now question is that, if you give me a mixture, what will happen? Say you give me a mixture of DMF, methanol, acetonitrile and DMS, what will happen? The wonderful thing we have observed is that our molecule takes exclusively the solvent or the molecule which is having highest polarity. Means if you give me all these four solvents together, as DMSO is having highest polarity, DMSO will be inside the pore, remaining all others will be left outside. So it is not only detecting, it is also like particularly capturing in a preferred manner. Okay, it is selectively separating and capturing the chemicals based on their polarity. Now when you did the experiment with the fluorobenzene, chlorobenzene and bromobenzene, see, if you see these chemicals, you cannot identify them just by looking at it, but you expose those chemicals to our molecule. See, there is a very distinct color here. All three different colors are different, and you can conclude, once you know the standard, you can conclude whether it is actually fluorobenzene, chlorobenzene or bromobenzene just by seeing the color. Now again, if you put them together in a mixture, how is it possible for me to separate them out? Our material will separate them out. The first molecule will come inside is the highest polarity molecule. In this case, it is chlorobenzene. Remaining all others will be left outside the like our material. So this material can selectively detect, selectively like encapsulate a particular chemicals amongst, like, no, in others, although they're in the same class based on their polarity. So we have the single crystal structure, and we have identified the position of each guest molecule inside the pore. I am not going into the details. Now coming to the another class of molecule which are in heterocycles. If you see diethylamine, triazine, pyridine, all of them are giving very distinct color, and also they can be separated based on the their order of polarity inside the cavity. So not only solvents, not only halobenzene, this material can also detect, can also identify and separate this class of material of N heterocycles. Now we have the crystal structure, we have the position of the guest molecule inside the pore. This is if the students probably don't know, it's not easy to get single crystals like these, but in our case, you just have the molecule, give exposure to all these different chemicals, the single crystallinity remains like retains, and you can characterize your molecule by putting into the X-ray diffractometer, and you can identify, you can see all the details of the structural features, including the position of the guest molecules inside the cavity. So this is another very wonderful phenomena. Now, coming to the nitroaromatics, a lot of work is going on all over the world to detect the nitroaromatics in a most convenient way. And you always, you know, that nitroaromatics are highly explosive, and it is always takes time to find out the nature of the explosive. Particularly, you know, the TNP is very highly explosive. But in our molecule, when you put expose our framework, this is a one unit of the pore. Okay, you don't get confused. I am not showing whole framework. This is just a small unit. These are the copper, these are the ligand, and this is one unit. Now, when you give nitrobenzene, when our MOF is exposed to nitrobenzene or 1,4-dinitrobenzene, okay, both are nitroaromatic, but see the color change. Here it is like almost red, and here it is green. Okay, so although they're in the same class of compound, but their distinct change in color can tell you that which one, whether your explosive is a just a nitrobenzene or 1,4-dinitrobenzene. Okay, and similarly you can separate them out based on their increasing order of polarity. Similarly, when you we have also have done many other study. I'm not going to show you all the results here. It is chloro-dinitrobenzene, like our molecule absorbed chloro-dinitrobenzene, 1,2-dinitrobenzene, 1,3-dinitrobenzene, and finally the most explosive one is a trinitrophenol, picric acid. So these are all explosive, but when you expose our metal organic framework to these different, you know, nitroaromatics explosive, just by seeing the color, you can identify the actual chemical nature, or the identify the species, basically chemical species here. Okay, which is not possible so simply. You have to do NMR or some other characterization. So our material can easily like distinguish even between different nitroaromatic explosive just by showing different color. Now I am going to another angle of these applications of metal organic framework, which is known as a proton conduction. So what is proton conduction? Why it is important? See, proton conduction you need when you design a fuel cell membrane. What is fuel cell? Fuel cell converts chemical energy to electricity. Okay, how it does? It's a very simplified diagram of a fuel cell. In the fuel cell, in one side you give hydrogen, H2. Hydrogen comes in contact with a catalyst. Actually, this is the anodic part of the fuel cell. Hydrogen become H plus and release the electron. The H plus move through this membrane, combined with the oxygen available in the other side at the cathode, and forms water. And the released electron here is connected with a circuit. Okay, this electron travels through this pathway and gives you the electricity. So what is the challenge here? Okay, hydrogen can be split into H plus and electron. It can also combine with the oxygen over here to give you the water. Perfectly fine. So what is the problematic part here is that this proton exchange membrane, this membrane should transport only H plus, not water, not electron. And it should be stable in presence of water, because you know it should keep in touch with the water molecule. Okay, do not forget, this membrane has to be conductive to H plus. It should not be conductive to electron. It should be stable in water, and it should not also conduct water. Okay, so these are the design strategy of any fuel cell membrane. And if you know this term fuel cell, which as I mentioned converts chemical energy to electricity, now it is very expensive, and the most expensive part of any fuel cell is the membrane part. The most widely used fuel cell membrane is made of naphthalene. Naphthalene is nothing but a polymer made up of like fluorine and sulfonate group, which is very stable in water at high temperature and conducts this like transport this H plus. But problem with the nephene is that when temperature goes above 80 degrees centigrade, its performance start deteriorating. Okay, and if you see its conduction level, just remember this number, 10 to the power minus 2 Siemens per centimeter inverse. It is higher or like it is, if it is a any material having 10 to the power minus 2 and above is a good or super protonic conductivity, we say. So our plan is to make some fuel cell membrane material which will conduct proton in this range 10 to the minus 2 Siemens per centimeter inverse or above, and it should be stable at higher temperature. It should be stable in presence of water. So what we need, first of all, what we need in terms of chemical, like chemical design, is that in any material you should have a carrier inside the pore. Carrier means proton is has to be carried now. So there are two different mechanism for proton carrier. One is called is hopping mechanism, means you have a carrier for H plus, means H plus can be given for one molecule to another molecule, to another molecule, to another molecule. So it has to be connected, the carrier should be connected via hydrogen bonding in a one dimensional channel. Or another possibility is that vehicle mechanism where carrier themselves move from one direction to another direction. So if you imagine this side is anode, this side is cathode, so carrier has to move like this from this side to this side by themselves. So you need a one dimensional passage containing some proton carrier, right? Whether it is this mechanism or this mechanism, bottom line is that you need proton carrier which are running in one dimensional space, and this proton carrier should be preferably formed via hydrogen bonding, right? Therefore it can easily carry H plus. Now when you study our molecule, so this is the crystal structure, and if you see these balls, these are actually position of the DMF on acetonitrile. You can see they're very nicely connected in one dimensional space. It's the same material I am showing you when we have the solvents inside. Now if you see diethylamine, if you see these balls, they are very nicely connected in one dimensional space. Okay, so we were very hopeful, okay, maybe they may connect, they may carry some proton because they're all in one dimensional space connected very nicely through hydrogen bonding. This is for water. If you see, these balls are actually position of the water molecules, they're all connected in one dimensional space. Same thing here, dinitrobenzene, DMSO is connected in one dimensional space, dinitrobenzene, nitrobenzene, almost in everywhere. One thing is common is that the guest molecule inside the cavity, inside the passage, inside the channel of these porous frameworks are very nicely connected in one dimensional space. So we decided that let us try our luck to see if this our material can conduct, like can transport the protons. Okay, so before that, as I mentioned, it's always like if you talk about the material application, these molecules has to be stable in presence of water, and they should have working temperature at least up to 150 degrees centigrade, because it generates heats. So when in this whole chemical process goes on, it generates heats. So your material should be stable in presence of water at high temperature. And here is the result. I am not going to explain because I understand many students are here. So what do you learn from here? Whatever is the peak position from starting to end, the powder XRD patterns are more or less remain same even if we keep our sample in water up to 30 days. These are the original simulated one. This is the freshly prepared. This is after 5 days, 10 days, 15 days, 20 days. So even if we keep up to 30 days, our samples are stable in water. Not only that, the molecules are stable up to 150 degrees centigrade here. Up to somewhere here, there is not much change in the powder XRD pattern till 150 degrees centigrade, tells us that this material is stable. The structurally this material is stable up to 150 degrees centigrade. Therefore, we can use this material as we can try to see if this is a good proton conductor for practical application. Okay, Now, when we have studied, we have seen that this is the framework, these are the guests, and when we expose to water vapor and measure the proton conductivity, we have seen that this is in the order of 10 to the power minus 3 Siemens per centimeter inverse. You remember the proton conductivity was shown by Nafion was in the order of 10 to the power minus 2. Still, it is not the best result, but it is showing one of the best result reported so far, that the proton conductivity goes up to 10 to the power minus 3. And this bar diagram shows you that different guest molecule, different conductivity. Only MOF, it's very less. Then we give diethylamine, we give dinitrobenzene, we give nitrobenzene, and the different guest molecule, different conductivity. And G1 triazine gives us the highest conductivity, or proton conductivity. The red bar showing here G1 means TZ means triazine. So therefore, we are very successful to achieve very high proton conductivity in this molecule. But we are not very happy with the result. We thought, okay, let us do even better. Why we should not go up to 10 to the power minus 2? We achieved only 10 to the power minus 3. So what I have done here, we found that this pyrazine molecule, you know that pyrazine is a Lewis base. You have two nitrogen here. We thought, okay, we have pyrazine. So if you give some Lewis acid, like inorganic acid, HCl or H2SO4, what may happen? These nitrogens can form a hydrogen bonding network inside the cavity of this molecule. Okay, if it is so, obviously the proton conductivity will increase, and most of the proton conductivity studies are done in presence of water, because you need a lot of carrier inside. But we have pyrazine already inside. Now if you give some acid, it will form a salt, right? Like pyrazine H plus. So you don't need water molecule. You already have free H plus, a lot of H plus inside the cavity. Therefore, it can give you wonderful proton conductivity. This was our assumption, and we have done the experiment. And first of all, the problem may come when you give exposure of this sample to the acid. There is a high chance that the molecule get destroyed, may get disintegrated in presence of very strong inorganic acid. But surprisingly, our material is stable. Powder XRD pattern tells us the material is stable even up to 12 non-band HCl. Nothing happened. Okay, for 6 hours. So it is perfectly fine. We can comfortably expose this material to the HCl to form some salt inside the cavity to get higher proton conductivity. Now, once we expose to different acid, one beautiful thing is happened. So this is the freshly prepared sample. This is when you give the pyrazine. What is the color? Red. Now when you expose to HCl, it's intense green. When you expose to sulfuric acid, it is light greenish yellow. When you expose to phosphoric acid, it is becoming brownish yellow. What is the conclusion here? Now this material, when I have pyrazine inside the pore, it can distinguish between different inorganic acid. You don't need to tell me, give me a colorless liquid. I'll tell you whether you have given me HCl, sulfuric acid, or phosphoric acid. There was a problem in nitric acid. Actually, the material was not stable in nitric acid, so we are unable to report it. But here it is very clear. This beautiful material can distinguish between different inorganic acid, just the naked eye detection. You don't need to do any experiment by using some very expensive instrument here. Okay, you give exposure to different acid vapor, it will take a particular color to tells you what is the unknown acid we have given. Very perfect, very good. Now when we expose, like this is the summary of the results of this part. So this was my framework. Now I put the pyrazine. So now I have pyrazine inside the cavity in this right hand top picture. Now when I expose to H plus different inorganic acids, now it forms a salt inside, pyrazinium salt. Now these pyrazinium salts by nature, they form extensive hydrogen bonding. Now when they form extensive hydrogen bonding, you do not need to give even high humidity. Generally these molecules show conductivity at a high humidity because you need to give a lot of H plus inside for conducting proton. But in our material, beautiful part is that you do not need to give any H plus. Still it shows very high conductivity. For example, This result at the order of 10 to the power minus 2, very close to the Nephion, is 0% relative humidity at 80 degrees centigrade. When you give the very high humidity, 95% humidity, it's almost same, very little different. What has to be noticed here? 0% humidity also gives 10 to the power minus 2 Siemens per centimeter inverse photon conductivity. And if you give exposure, anyway, it will be giving you at the rate of range of 10 to the minus 2 Siemens per photon conductivity. So it is one of the best material, like the molecule I have shown you so far is the one of the best material in many different sense. So let me conclude, like summarize and conclude my talk. Whatever I have demonstrated in terms of our work, we have demonstrated a colorimetric detector for the widest variety of small molecule reported till date. Okay, there is no such molecule reported as of now which can detect so many numbers of varieties of chemicals starting from solvents, nitroaromatics, heterocycles in a reversible and single crystal to single crystal transformation mode. Means single crystal means you can also detect the molecule from the X-ray crystallography, the position of the molecule inside the pore. The same molecule shows the superprotonic conductivity, as I have just mentioned in the last slide, and may have, this molecule probably have the potential in a application in a fuel cell membrane for practical applications. Now coming to the like background, like who are people who have contributed most in this area. Susumu Kitagawa from Japan, Andrew Cooper at Liverpool, Gerard Fede, he recently died a few years back, Wen Bin Lin at Chicago, Jeffrey Long, Omar Yagi. Actually, Yagi is the person who who started using this term of metal organic framework. Earlier, people tell it coordination polymers, something else, but this MOF term is being coined by Yagi, and it is, this is very often you can see this term in many research paper. Wangkai Zhao at the Texas A&M, Jetty Half, and many more people, even in India, many groups are working along this line. And finally, acknowledgement, most of the works are done by Sajal Khatwa, Kupil Tomar, Himanshu Jana, Arun Bhatt, and many people in my group. Fundings are from CSIR and ISR Bhopal. And I thank you all for your time and kind attention. I'll be glad to answer any question from your side. Hello.
Yeah, thank you so much, sir.
Javed, how are you?
Yeah. Thank you.
I'm still live. I'm still live because I'm unable to now.
Because
I am struggling again.
we have question answer session. So thank you so much for such a informative, enthusiastic, and it was a very nice talk. If I see from the students' perspective, you explained it very beautifully. Sorry, from the participants. And the first question is, sir, if hydrogen fire is far safer than gasoline fire, why don't we use the process of electrolysis of water in order to use hydrogen as fuel in day-to-day transport system?
The answer is that, see, hydrogen, you need, as I mentioned, 3 kilogram of hydrogen you need to run a car for 400 kilometers. Okay. Hydrogen generation or availability of the hydrogen is not a problem. Problem is here is the storage and release. Okay, you have to store it and you have to really release it slowly. Okay, you can, electrolysis, you can generate hydrogen, or you can even hydrogen can be available from many different sources. Okay, that's not the problem. You know, in your vehicle, you cannot do electrolysis, generate little bit of hydrogen, and run the vehicle, right?
Yes.
So main challenge is there is the storage.
Storage is a problem.
Okay, a certain amount of hydrogen you have to store in the vehicle to have its practical application. Otherwise, it should not be like commercially viable, basically.
I mean, we need a very big vehicle for that.
Yeah, you have a
right?
very big vehicle. Otherwise, it will create a lot of pressure. Okay, that pressure will be, it can explode even at high temperature. Therefore, you have to put some frameworks molecule inside which will store more amount and create less pressure. Okay, am I clear?
Yeah. The second question is regarding proton conduction, and the participant says like, what will happen to the proton conduction if low temperature is there?
Low temperature, see, there is a optimum temperature of like, see, if you talk about running a vehicle, okay, generally we study room temperature and above. The reason is that when it happens like this in the let me rephrase it. I'm little bit okay. The question was that what will happen at the low temperature? Definitely proton conductivity will be less. Okay, in the fuel cell membrane, proton conductivity will be less if you decrease the temperature, because you need some kinetic energy for the movement of this proton. Okay, I have not highlighted the kinetic energy part. Okay, but if you decrease the temperature, you're giving less amount of energy, therefore proton conductivity will be less. But the important part here, this fuel cell, they generate some temperature. There are some chemical process happens which is exothermic. Okay, therefore we don't think temperature will be really low. It is always the high temperature that is a problematic. You understand? Because it generates 100 degrees centigrade in the inside the fuel cell.
Yes.
So if the practical application, you do the low temperature may not be a problem, because fuel cell itself will generate a lot of heat. You get my point?
Yeah.
So for practical application, problem is the high temperature rather than low temperature. If it is, you say, for example, if you try to run it in Srinagar, okay,
Yes.
I understand temperature will be less, but when you switch on the fuel cell, the chemical reaction will generate a lot of heat. So it will reach to the above room temperature very well. Only problem will be that it will go up to, if it goes up to 80 degrees centigrade, the performance of the membrane goes down.
Yeah.
So problem is there, not at the low temperature. You understand my point here?
Yeah.
But for sure, low temperature will contact less. There is no doubt about it.
Yeah. So another question is from one of the faculty members, like participants. Are weak interactions all enough to stabilize the guest molecules in the MOF?
100%. There is no doubt about it. See, in our case, the framework is mostly made by copper and ligand, right? Now, if you see, it is actually two-dimensional. And beauty of the molecule is that the two-dimensional states are interdigitated by slow, like weak interactions. Why this molecule is so versatile? Because, and why it is taking so many different guest molecule, is that the molecule can breathe. Means it can go expand, it can contract. It can expand, it contract. This is only possible because these two-dimensional sheets are connected via weak interactions. If it is connected via covalent bond or coordinate bond, this was not possible. Okay, to accommodate so many different types of guest molecule. It's because they hold together, they are held together via weak interactions. Now question is that whether the weak interaction is good enough to accommodate guest molecule inside the pore. Definitely yes, no doubt about it, because we are not talking about only one bond. They are connected with each other through extensive weak interactions like hydrogen bond pi interactions, and that is no problem at all to localize them inside the pore. Okay.
Yeah. Keeping in view the pore size, basically, like pore size should be more important, and then weak interactions will play their role.
Yeah.
Right?
Yeah.
So are you ready to take some more questions?
Yes, I am. Yeah, no problem.
Okay. So one more question is MOF'S in drug delivery as a potential anti-cancer drug delivery vehicle. So, like,
you can do it. There is no problem. There are some problems with the MOF is that, see, these material are framework structures. Okay, framework structure means they are not soluble in. Is Javid, I am sharing or not sharing?
yeah.
I was actually Zoom. I am using for
Yeah,
the
yeah, it's
second
still,
time.
yeah,
I get confused. I am now still looking here and there to see what to do. Okay. See, for drug delivery, it is in human body, right? For drug delivery, it has to be water soluble. And 90% of the framework structure, actually, they are kind of polymer, right? So they are not soluble in water. And water is the only biocompatible solvent, right?
right.
So therefore, there are some research going on. Some groups are doing it, trying to do it. You can encapsulate the drug and try to deliver it. But there is a huge practical problem. Most of these MOFs are not soluble in any solvent. Forget about water.
Right. Yeah.
If they are not soluble, how do you inject into a into biological system where only solvent is the water?
Yeah.
Therefore, it is some groups are working fine, but it is practically, I feel it is not
Yeah.
possible.
Solubility is the main issue.
Very big issue. Okay,
So
now
I think one last question. That's how do we differentiate MOF from an organometallic compound?
see, organometallic is a totally different class of compound. Here, you're connecting a ligand in a both side or three different side, four side to make a framework. It's a repetition. One unit connected with another unit. You have a ligand at 180 degree. This side is connected. This side is connected. And now metal is further connected to the other side. It keeps going on. It's kind of polymeric structure, having well-defined pore. Organometallic is a totally different class of compound where metal are different, ligands are different. What is the difference there? In organometallic chemistry, metals are low valence. Metals are connected with carbon, phosphorus, or certain number of donor. Metals are, just not a framework. It's a discrete molecule. Organometallic complexes are not framework structure. They're discrete molecule where metals should be at the low valency. Metals should be connected mostly with a kind of covalent connection with the carbon or phosphorus or some selected donor atoms. So organometallic chemistry is quite different compared to this kind class of framework structures. Their framework is non-existent. Okay, and here we don't care about the oxidation state. We don't care about the donor atoms.
And we
Chemistry is
don't
quite
have,
different. Okay.
we don't have a metal carbon bond in MOFs mostly, like as compared to the organometallic
Not only
compounds.
carbon, then that it will be phosphorus also. It could be some other things also. But there is a well-defined separation between organometallics and any other coordination compound. Okay.
Thank you once again, sir, for your very informative talk. And on behalf of the department and college, I like invite Professor Hina Kadri. She will be presenting the vote of thanks.
Ladies and gentlemen, a very good noon to all. I, Hina Kadri, Assistant Professor, Department of Chemistry, on behalf of my department, would like to pay my heartfelt thanks to our worthy principal, Professor Dr. Yasmin Ashai, and the organizing committee of the college for providing us a chance to organize this webinar. Special gratitude goes to the resource person, Professor Sanjeev Konar, for the highly knowledgeable and informative lecture. I once again thank you, sir. I'd also like to thank all the participants, especially the faculty members and student faculty, for making this webinar a success. Thank you.
So thank you, Professor Kadri, and I really appreciate for the opportunity given to me, and thank you very much.
So with this, we conclude the session.
Thank you very much. So should I disconnect, madam?
Okay, sir. Thank you so much.
Okay, thank you. Thank you very much.
question and answer session goes